All right, it wasn't quite 10 minutes. We're kind of running out of time, and people have made arrangements. So let's try to get the remaining content on its way. Before I hop over to the last session, just a couple of clarifications. There were a lot of really good questions today, and when we actually started working with R and trying to specify priors, I could see there was a lot of difficulty in understanding certain concepts and applying certain concepts. Many of the questions that you asked were about distributions and assumptions about certain distributions and what kind of, for example, measurements fall into different distributions. And there was another whole family of questions that seem to surround the concept of the linear model and how a linear model, what parameters a linear model estimates. As we said at the beginning, we unfortunately cannot cover this content. This is part of a general education in statistics, which we obviously, unfortunately, in our field very rarely can enjoy when we do our degree, right? So that's really, really tough. However, we need to know these things when we want to critically evaluate our assumptions when we do these hypothesis tests, when we do these quantitative assessments of our hypotheses. Right? Again, I highly recommend an introduction book by Bodo Winter. For example, there are other really good books out there and good resources, but these things will pop up again and again and again, and having a rough understanding of different distributional types and of how a linear model works would really, really benefit you in applying these Bayesian methods to your own research. Okay. Now, we will dive into the last session and we'll remind ourselves what the differences are between null hypothesis significance testing versus Bayesian inference. And here I want to stress practical concerns. And I do that because I ended up being a Bayesian because of practical concerns rather than philosophical ones, right? So comparing null hypothesis significance testing and Bayes inference is comparing the tools that we have access to get a particular job done. In our case, you want to answer a research question. NHST and Bayes are two different tools that might be used to answer research questions. And until now, all of us have used the X, null hypothesis significance testing, to answer research questions. But now here we offer you a new tool, Bayes, Bayesian inference. So it's worth reevaluating the difference between them. Some of the things have been said already and others were just implicit in our discussion. So it's really worth making them explicit here. First, these two things do conceptually very different things. Even though it sometimes looks practical very, very similar, they do different things. They both estimate a probability, yes, but NHST is, well, at least I said, it's a little weird. It estimates the probability of seeing the data or more extreme data if a null hypothesis was true. So the hypothesis is already given, and we merely estimate the probability of observing what we have observed. Right? Bayes, on the other hand, estimates the probability of a hypothesis that is specific parameter values of our linear model, for example, given the data at hand, given what we've observed already. So the hypothesis, the thing we're interested in, is not given, but the thing that we want to estimate. What is given are the data, the facts, what we have observed, right? What we have experienced so far. And this difference might sound minor, but it's not really. Consider the following example. The probability of being dead, given that you have been decapitated by a shark, is close to 1. Right? And it's really unlikely that you survive that wound, right? But the probability of being decapitated by a shark, given that you are dead, is actually close to 0, because there are many different ways to die, and getting eaten by a shark is only one of the many ways to die, and it's one of the rarer ones, right? Bottom line, these two tools measure quite different things conceptually. And one big question is, of course, that is, what is it that we're interested in? Do we want to know how likely the data are if there was nothing to be found? Can be argued that this is a valid way to look at it. Or do we want to know how likely our research hypothesis is, given that what we have observed in our data? I personally resonate much more with the latter, right? So here I summarize the main conceptual difference again. Again, first, and to repeat, Bayesian inference estimates the probability of parameters based on data. So instead of assuming a null hypothesis and calculating the probability of the data, it calculates the probability of different hypotheses given the data. Huge difference. Second, Bayesian allows you to incorporate prior knowledge. Null hypothesis significance testing traditionally does not. Third, Bayesian also yields directly interpretable estimates of probable values, of plausible values in the parameter space. These are more intuitively interpretable in light of our alternative hypothesis, right? Bayesian inference does not give us a p-value, long-run probabilities of committing a type 1 error. Instead, it gives us a probability distribution that are based on what we assume in the first place, the prior, and what the data can tell us, the likelihood. Right? There is no inherent cutoff decision in Bayesian inference. You can, and we will talk about it, you can introduce them, but they're not inherent. And finally, and Joseph touched on that earlier, NHST estimates one true parameter value. Bayesian inference yields a distribution of plausible parameter values, the posterior distribution. So those two frameworks differed in a principled way, right? But again, if you're not a purist, if this philosophical difference is not particularly relevant to you, let's look at what it means practically. Practically, that is the way we use these tools. They seem to be quite similar. So why would you want to switch to a new framework? How can I convince you to do so? Let's talk about the practical advantages. Here's a list, and then I go through it step by step. Bayesian inference is very flexible in terms of model architecture, especially with our beautiful BRMS package. We'll get to that later. It's not limited by these very specific optimization constraints, those convergence failures that you find when you use LME4. They're not limited to categorical decision procedures like thumbs up, thumbs down, significant or not significant. They are, however, computationally expensive. They add another layer of researcher degrees of freedom with priors, and they require much more thinking. They're much more involved. So let's go through this real quick, step by step. First, Bayesian modeling is tremendously flexible, allowing us to do everything we need to do with one and the same tool. And that means here, one and the same R package. It's beautiful. We can model different error distribution, Gaussian, binomial, beta, ordinal, multinomial. Okay, so despite often using simple Gaussian assumptions, we also measure a lot of things with different error distribution. We look at forced choice data, we look at multiple choice data, we look at Likert scales, ordinal data, right? Response variables are often also not normally distributed, but assume kind of a log normal distribution. And we will get to that tomorrow with more on priors. Second, our analyses differ in the required level of covariances. Some of us need simple or multiple regression, the ones that we just used in the example earlier in the exercise. Others, and that's probably most of us, excuse me, it's raining here, I need to shut the door. Most of us actually use probably multi-level models, right? Mixed effects models. Third, while often focusing on one measurement only in univariate models, there are actually many scenarios where this is not reflecting the conceptual nature of our research question. If I'm interested, for example, in the acoustic correlates of word stress, I will probably measure more than one acoustic correlate. I would probably look at duration, intensity, fundamental frequency, right? And I want to predict whether these acoustic correlates differ in different positions of the word, right, in different syllables. A multivariate model might be more appropriate. It takes all these measurements into account at the same time and their correlation with each other. Our BRMS model can straightforwardly do that, no problem. So the tools that we are advertising here, BRMS and specifically, they're very flexible and they can be tailored to your research question, rather than, let's be honest, the research question being tailored to our tools and what we can do with these tools. How often did we find ourselves not being able to do what we actually wanted statistically, right? For those of you who have used the now standard learnB4 package for linear mixed effects models, that are a bunch of you probably, to run their linear mixed effects structures, you have suffered, like myself, from so-called convergence issues. These warnings, they let us politely more or less know that the iterative optimization procedure fails to reach a stable solution, which renders the model results uninterpretable, basically. This is bad, because that often means we have to change our model specification and simplify our model. The planned model was most likely appropriate for the data at hand. For example, you might have data from different speakers and different stimuli. So you might want to add random slopes for both of these groupings into your model, right? If you don't do that, you risk underestimating the variance and the results cannot be trusted. Practically though, when we run learnB4 models, we often have to reduce our model, and we end up with models that have like an unknown high false positive rate. Again, rendering the results more or less informative as we would like them to be. It's bad, right? And from my own experience, convergence issues are omnipresent. They happen all the time, definitely more often than not for the kind of data that I work with, which is probably similar to the data that you have worked with. I basically never was able to run the models that were appropriate for my data structures. And this was the single biggest reason to move to Bayesian land. I'm not a purist, or I was not a purist. It was mainly a practical decision for me to run the models that I want to run. Bayesian estimation does not run into these particular convergence issues. There are some convergence issues. Joseph is going to talk about it tomorrow. But in this scenario, our priors actually help us technically to fit the model, to find its way through the vast space of possible values. Bayesian models can have their own convergence issues, as I said, but we are not constraining ourselves anymore. We don't have to reduce our model structure anymore. We can run those models that we think are most appropriate for our research question. That's a huge pro in my books. Again, do you remember our example on probability of rain, right? The big practical question, the big consequence of our estimation was a decision to act. Do I bring an umbrella or not? And this is conceptually comparable with what we do using null hypothesis significance testing in our research. We collect data, we apply statistical procedures, and we just want a binary answer to our question. Thumbs up, thumbs down. Are there meaningful differences? Now, this decision procedure is inherent, again, in null hypothesis significance testing. In Bayesian world, it's not. You can introduce a decision procedure, of course, but it's not inherent to the approach. And tomorrow you will learn at least 3 different ways how to evaluate evidence continuously rather than using a decision procedure. What we do in Bayesian analysis, we rather estimate uncertainty based on the data, the model, and our prior beliefs. We make an educated guess as to what constitutes plausible values, right? That's what we do. A drawback, if you want, comes with this kind of approach, of course, because there's no hard cutoff decision. There's no thumbs up, thumbs down decision procedure. And evidence is considered a gradual probability function. We have to think more about our data and our interpretation. That might be considered a practical disadvantage for some. And I get it. It's very involving. But for me personally, that means more engagement with the research question, the quantitative nature of its answer, and the quantitative nature of the system I'm investigating. Being Bayesian means thinking quantitatively. It's a good thing in my book, right? It gets me more in touch with my data and my research. Another big practical drawback, and I need to mention this here, is that there's really no hedging around this. Bayesian models are computationally expensive. And if you have a lot of data, you have a complex model with many parameters to estimate, for example, complex linear mixed effects models with a lot of grouping factors, sampling from the posterior will take a long time. For certain models, we might need to outsource that computation. In most of the cases I'm dealing with recently, in 2020, 2019, my models ran overnight on my machine. Okay, why is that? Well, when it comes to models with many different parameters, solving Bayes' theorem might become computationally intractable. However, there are clever ways to circumvent this by approximating the mathematical solution via sampling. Joseph will tell you more about this by the end of day 2. I won't go into detail here, but this approximation process, that is the sampling, is computationally very expensive and time consuming. Now, this is obviously a practical limitation. Having said that, the way that BRMS and Stan in the background is working recently has improved tremendously recently. It works much quicker than before, and it's constantly improved. Our machines obviously constantly improve. So this limitation is real at the moment, but it looks like it gets better quickly. Another often articulated concern is that Bayesian analysis comes with more degrees of freedom. And looking at the Q&As from earlier in our discussions, this is certainly a concern that you have, right? The priors need to be specified. We didn't do that before. Now we have to specify priors and we have to make decisions, right? We do specify priors, but mostly, and you will hear about that tomorrow, we restrict ourselves to defining so-called weakly informative priors. That means they will not have a large effect on our conclusion. And these priors are not particularly flexible, right? They are usually centered on zeros, as Stefano has already mentioned it, and they allow a wide range of numbers. They're not biasing the posterior. They're not dominating the posterior. That's lingo in Bayesian land. The likelihood dominates the posterior, meaning the likelihood, the data that we observe is mainly determining where the posterior will be. Right? And since we do not do hard cutoff points and decision procedures, you know, the minor difference in the quantitative probabilistic assessments of our research questions, it's not a big deal, right? It's not that we, you know, if you change the prior a little bit, we go over the hump and suddenly it's something is significant. That's not what happens here, right? So it's less of a concern actually than it might be in a frequentist context. So overall, we still do something actually very similar as we did before. We make the best guess based on our model, data and prior beliefs as to what the world looks like. Bayesian inference does that in a much more intuitive way that is practically more flexible. It does make us have to think about things a little more, and it's computationally more expensive. But it also allows us to embrace a very central property of the world in our field of research, right? Uncertainty and the probabilistic nature of the systems that we look at, right? With regards to that, I think this is a huge, huge plus. Okay, this was our first day. Let's have a look. We're 3 minutes over, so that's not too bad at all. A reminder on our roadmap. We will start with a so-called review tomorrow at the beginning, and I will most likely do a live coding session with you where we go through the process of setting up a very simple linear model again, specifying the priors, look at what these priors actually mean, and also what the output of the model actually tells us, right? So we will really go step by step through this process to make things a little bit more concrete for you. Then we will talk about inference, how we can do inference without a decision procedure. And we talk more about priors and specifically weakly informative priors. What is that? How do we specify them? And then we will do another coding session together where we actually run a mixed model together, right? Where we specify all the parameters, all the priors for the parameters in the model, and we actually run it and interpret the results. And at the end, we have a peek under the hood, what sampling is like and what we actually need to keep in mind with regards to that when we build our models. And then we think it's a wrap and it's a coherent package to get you going. Okay. So for now, that's it from my side. Stefano, Joseph, anything else?
No, I'm just going to quickly answer a question that is very interesting. Somebody asked, how does effect size and statistical power fit into the Bayesian framework? And we will just briefly touch upon that. But differently from frequentist models like LME, for example, effect size and sample size are reflected in the posterior, meaning that while with LME, a small sample size is highly problematic, with a Bayesian model, the uncertainty that derives from the small sample size is reflected in the posterior. So basically the posterior embeds the fact that the sample size probably was not appropriate. But we're going to go back to this tomorrow.
Any other urgent questions that you guys picked up in the Q&A that we might want to cover now?
Not that I can see. I did answer a few on Slido, but we are going to actually make sure that we're going to go through the questions that have been asked and pick the most upvoted ones and go through them tomorrow during the review.
All right, I see people leaving already. Thanks everyone for being here, and let's see you tomorrow, same time. It was a blast so far. I hope you're still pumped for tomorrow. You guys quickly staying? Joseph.
Yeah. Yes.
There's a thunderstorm brewing here, and my office just became an inferno. Maybe we should switch to a different channel.
Yeah, I think we could close this one down.